Welcome everybody to the 3D scanning and motion capture lecture. Today we're going to talk about bodies and hands. And as usual, I would like to start with a quick recap about the things we've talked about in the past lectures. The main theme in the last 2 or 3 lectures was essentially that we talked about dynamic 3D capture. We had these different axes from domain-specific capture to freeform capture to freeform tracking. And specifically, we talked about phases a lot. We talked about these parametric phase models that essentially allowed us to get a dimensionality reduction from a parametric phase model. And we later on talked about how to use these phase models for tracking. And as you remember, in these models, we had the shape identity and we had a PCA essentially that defined the variation in the shape. So you could have one set of axes for the shape parameters, one for the albedo parameters, and one for the expression parameters, and so on. And we then had essentially constructed a phase model. And this phase model we constructed from a large database of 3D scans. But essentially we had this model. This model had geometry, albedo, expression, illumination, and pose parameters. And this essentially was this lower dimensionality approximation of real-world faces. And the idea then was, once we had this parametric phase model reconstructed, and it was quite an effort to do it, then we could go ahead and fit this model to some target observations at, well, let's call it test time or run time. And then this fitting at observation time there was essentially based on energy minimization. So we had a variety of different terms. And I'm going to repeat this quickly because I think this is pretty important. So in this case, we had sparse terms. These are facial landmarks, right? And we had dense terms such as pixel photometric losses and geometric losses. And the idea was we could optimize for these using the solvers we talked about before. In this case, we talked about using Gauss-Newton solvers or possibly LM solvers in order to get this done fast. And it turns out at the end of the day, you could even do, like, since this parametric phase model is a image formation model, we could even do RGB only tracking, and we could get reconstructions that look like these ones here, right? So we just have a video feed as input, and from this video feed, we could reconstruct the geometry. And the ideal objective of this optimization is that every pixel here matches with every pixel here in the video respectively, and then we can have this 3D reconstruction or 3D tracking of the face template using only an RGB video here as input. Okay, so now we talked about faces a lot, and the other important things we would like to talk about today is bodies and hands. I mentioned this already. So the idea, in a sense, of these parametric models is very similar to what we have had for faces. So for bodies, in order to get it to work, for hands, the same thing, right? The idea is we want to have these parametric models right now that do this dimensionality reduction. And the roadmap here is very similar, right? We take a set of scans from a variety of subjects, we non-rigidly align them with a template to obtain consistent topology, and then often the parametrization in this case now is with respect to an underlying skeleton. And this part here at the bottom is kind of the key difference, what we will mainly talk about today, because now we have to figure out how do we get better control, right? For faces or so, it's not so, it's kind of this abstract PCA space. It's not such a bad control because it allows us to edit or control expressions and shape and appearance and stuff like this. But for a human body, for instance, or for a hand, we typically have an underlying skeleton, and we would like to parametrize, or we like to embed this skeleton as part of the parametrization. And this is what we're going to do today in this lecture. We're going to talk about methods like this. A fair disclaimer, I took a lot of slides from Gerard von Smol. He's been one of the leading researchers for virtual humans. He's at the University of Tübingen, actually. So he and his group work a lot on this one. So credit to him because I took a lot of his slides. So the core idea here of these parametric models is, as I said, it's the same idea as for faces, except we want to add the skeleton to it. But let's make it more concrete, right? So we have here this model here again, This is our model M. We have a bunch of parameters that we want to feed here as input, and what we want to like to get as output here is we would like to get a 3D mesh as output. And 3D mesh as output in practice means we want to have a set of vertices, similar as in the face models, right? We had this template face model where it had a bunch of vertices, and we want to, based on these parameters, know where these vertices should go. And these vertices might also have attributes such as colors. We could debate a bit what's the right parametrization now for the RGB. Is it on a per vertex basis or is it on a per texture basis? For the most part, we're going to talk about vertex colors though for the time being. However, this is already a few years older, so this research is like 5-6 years old. There's already a bunch of stuff right now that uses even neural networks to parameterize colors and so on. But that's not what we're going to talk about today. Today we want to get to the basics because that will help us later to understand more fundamentals. Okay, so what are the parameters here of our face model, right? So we have a couple of them. We have pose here. This is our theta, and this theta here, when we are talking about pose, typically in 3D scanning setting, you would typically expect, oh, this is like a rigid pose also, right? But in this case, the pose is actually the skeleton pose. We want to use that to parameterize and to animate possibly the human, right? So for instance, the idea is we have this parametric model, then we have a skeleton tracker, and we want to use that skeleton in order to animate or fit the respective skeleton, the respective human model. Okay, shape is very clear, right? What's the human, textures, the appearance, and then we have a bunch of hyperparameters we also need, and we'll get to this, what this means in practice. Okay, well, in practice, this is how it looks like, right? So now this is what our model should be able to do, right? We want to change certain things. We want to change, this is our 3D scan with the texture, right? This is our ground truth shape, this is our model, and this is our respective model with the texture. And now what we're doing is we can go ahead and basically change some of these parameters. So you see, for instance, here the pose is being changed a lot, right? So based on these pose changes, we would like to animate the respective model here. Okay, but let's have a more concrete example to this. So here are a couple of examples. So here we have our model. If we're adding in a 0 here, this means just we're in the default pose, and X is respectively the shape. This one here means if we have kind of an identity here, that means, oh, we are in the average human, but we have a certain pose that defines this pose here right now. And then we can combine these two, right? So now we can feed in a shape, feed in a pose that gets you that respective person, what we're fitting here in a shape, and we're getting here the pose, which defines the respective pose of the human body here, right? We can rotate it with a rotation matrix, we can texture it accordingly, and so on. So this is kind of the high-level idea, what we want to do. And all that is doing right now, it's essentially extending the face models we have been doing to human bodies. And the big distinction here is right now we have this notion of a skeleton. Please understand, okay, we have a bit of a different notation here, but in principle it's very similar, right? So we have this body model, which is essentially a function. We have a bunch of parameters as input, and this body model has been learned in a preprocess, and this preprocess that defines kind of the pose, shape, space, and so on. Okay, so how's it being done for the most part? Let's talk about maybe the early days, so to say, from human body modeling. And one of a very popular dataset here is the CESAR dataset. It's the Civilian American European Surface Anthropometry Resource Project dataset. And this dataset is essentially a bunch of people that have been scanned. These scans look something like this here, right? So you see you have different types of scans here. And the idea is that based on these scans, people wanted to understand the modeling the space of the human bodies, right? And the way these scans were obtained, they had these super cool laser scanners, these cyberware 3D laser scanners, right? They looked something like this, super high quality, super expensive to do also. And these are the scans that got as output, right? So, and this, as you see already here, this is like 2003. So it's like almost 20 years ago now. It's a bit shocking that this is already 20 years ago. But yeah, so this is basically when this research has gained a lot of momentum, when people had the ability to have high quality laser scans, of humans. One thing you will very often see in this space is that people are scanned with very little clothing. And the reason why people are scanned with very little or very tight clothing, for the most part, is that modeling cloth by itself is another whole area. We're not going to talk about this one right now. In this case, we're just going to talk about the modeling of the human bodies, but we're not going to talk too much about, like how do we deal with like cloth and then possibly physics animations of cloth and so on. This would be going a little bit too far for the time being. But as a consequence, right, you will see that these original scans that have people taken, they are mostly with very little and very tight clothing to simplify it. The other thing you will see is the hair is typically also very simplified. So in these 3D scans, you see very little hair for the most part. And there's a reason to it. It just makes the problem statement a lot easier. Okay, so now people have the ability with these high-end scanners to get these high-quality 3D scans. And based on that, what people do is, well, we want to compute a parametric model. We just follow the same procedure, what we have learned so far for faces. And the simplest thing we can do is we can go ahead and non-rigidly align, we do non-rigid registration essentially, right? So now what's being done here is, as you can see, right, this is like just take this template model. This template model is now fit to the respective target scan, and we are getting a non-rigid registration with the techniques that we have seen before. I'm not saying these are the same techniques that we have been introduced. This was a little bit earlier, so they at the time used linear deformations, I think. Probably not the state of the art. It's not using like RF or something like this, which people would use today. But methodology-wise, very, very similar to what we have been introducing at the beginning of the class, where we talked about like RF and ED deformations and used them as regularizers. This is probably what you would do today. Okay, and the scan of this one in this case is scanned with about 125. I think it's actually exactly 125 male and 125 female participants, and they have a variety of like ethnicities, ages, and weight, right? So you basically want to span the human shape space to a reasonable degree, right? But be aware, right now this is all neutral pose, right? This is all just the shape space. And the idea, basically, what people had been doing here, they also had annotated this data set with these markers. And these markers essentially then were used later on to control it. So you could, this not only help, I mean, I think the main reason why they did it at the time, they wanted to get the registration between the template models and between the different scans. But this also can be used later on to animate it, of course, because it gives you a prior on the animation part. Okay, but then, once you have the scans, once you have the non-rigid alignment, now what you can do is you can do the same trick what we had seen before. We can basically compute a PCA model. Very straightforward. You just take the template. You have this template for the first person. So you non-rigidly register this template to the first person. That gives you this vector of vertices. You non-rigidly register the second person. That gives you this vector, and so on. So you get one vertex vector of the template mesh, which is non-rigidly aligned to the respective human that has been scanned, right? And then what you do is you compute a PCA out of this matrix here, and this essentially gives you the variance in humans, in the human shape space. And since this is actually a PCA, right? Remember what the PCA is doing. The PCA is assigning the first principal component to the axis with the largest variance. And for humans, for the most part, what this means is if you're just taking the first principal component here, you're going to see a strong correlation to height and weight and stuff like this, right? So these kind of things will be very correlated here, right? So height and the first principal component is super correlated. And the reason why that is, of course, is this is like the most distinctive feature or the most distinctive variation in a sense what humans can be doing. Okay, and based on the PCA model, you can then deduce the most prominent features of human shape spaces and can vary them accordingly in the PCA space by reassigning or changing the coefficients to these basis vectors. Okay, and this is what you can get here basically, right? So this is like the you can change the height in this data set, sorry, in this parametric model, and you can change the weight accordingly. So this at the time was really cool, right? I mean, think about it. This is like early 2000s, and now you could have these two controls here, and you can change basically, or you can explore the shape space by changing the height and the weight of people accordingly and reanimate the faces. Okay, so this is relatively straightforward. So far, this is pretty much essentially what people have been doing on faces. And you can see actually it's interesting, right? This Blanson-Fetter model for faces was like, I think 1999 published, and this one was a few years later published. So people first did it for faces basically because this is a little bit easier to get the scans and so on, and then people did the same ideas for the human bodies. Of course, there's still a lot of things that are not being done yet, but also we haven't talked about skeletons, for instance. And this is basically one thing that people thought about afterwards. How can they use skeletons and so on? But it already allowed a lot of stuff to do here. So you could do morphing between different people, right? So you have like one human and another human. You fit the respective PCAs to it, and then you can interpolate between those two, and then you can morph between those humans. And this is kind of a really cool application, right? So this is at the time what people were looking at. So they were looking at this morphing part, and then they were trying to think about, oh, how can we fit skeletons to these models essentially, and then do retargeting. And this retargeting, by the way, this is I think what most people in computer graphics were becoming interested in, because they thought, oh, well, if we have a bunch of scans and we have this parametric face model, we then can essentially have virtual character animation, you know, for like video games and stuff like this. Okay. All right, so what have we talked about so far? So far we've talked about a PCA model that can be computed on a bunch of human scans. These scans were human bodies, all in a neutral pose from the CSAT dataset, but so far we didn't have any animations on whatsoever, right? And this is the thing what people have done afterwards, and this is a very popular paper as well. This is the SCAPE dataset, SCAPE method. So here the idea is essentially that in addition to the shape and the identity of the humans, now there should also be an animation, but the idea is that this animation should be somewhat correlated with respect to the skeleton. So this I think was one of the first papers that basically allowed both at the same time, right? So you could change shape and expression parameters for human bodies. Idea was to expand what CSAT had been doing. So now they had cyberware scanners. They capture 4 directions simultaneously, approximately 2K points per model, and then they merged the 4 scan views. In this case, what they did is they had 70 poses of one particular person in a totally diverse variety of poses, right? And for the identities, they had 37 different people in a similar but not identical pose. And this is what they added in addition to the original CSAT dataset, right? So they used the CSAT dataset essentially as a basis for the shapes, and then they added the additional identities and poses to it in order to get the kind of the expression variation, right? And then they reconstructed a skeleton. So they have 16 parts for each pose, and then they compute well, kind of like delta PCA-like blend shapes. So over each triangle, it tries to figure out with respect to the skeleton how it moves away from the average. And this is also encoded in a PCA. It's kind of like delta blend shapes. I'm not going to go into too much detail here because it's not probably how you would do it today. But I wanted to get you the high-level concepts. With all the techniques that we have talked about in this class so far, you should be able at this point to come up with a reasonable solution, at least with a similar solution that SCAPE did. Maybe not with the very best solution, but with something that is kind of reasonable, right? So you know non-registration, you know how to compute these PCA bases right now, and we can do this over both shape and poses, and you can figure out how to construct a model like this, right? And the only thing you have to consider is, right, how do you encode the expressions relative to the shapes respectively. Okay, yeah, but what they do is they have a basic skeleton. They compute delta-like blend shapes based on the PCA over the triangles with respect to the skeleton. Okay, as output, they get something like this. So they have here kind of the mean, and then they have principal components here respectively that can change the expressions here. Sorry, they can here change over this PCA here. They can go ahead and change the shape respectively. You see the pose here is always the same. And then they have different PCA axes, PC1, PC2, PC3, PC4. And each of these axes has a different effect in terms of the body shape, right? So for instance, this one makes you kind of like thick, like taller and smaller. This one is more like, I think this one is more like bulginess and stuff like this. But this is kind of, it's not semantic in a sense that somebody assigned, oh, this has to be this specific change. It's just whatever the PCA had found the most variation in, and then it's optimizing this lowering approximation in order to get this parametric model. Okay, but now with shape, with SCAPE, you could go ahead and also do animations, right? So now you could go ahead and have this template here. So there were these markers now. And now what you could do is you could change basically, you could change the poses, sorry, you could change the markers, and based on the marker changes, the skeletons would change, and based on the skeletons, you could then reanimate the whole thing afterwards. Again, I'm not going to go into full detail here because this is probably not something people would do today anymore, but I can highly recommend have a look at it. It's actually quite an interesting paper because they had a lot of engineering effort going on in order to figure out all the scanning stuff, and they got pretty plausible results. And their application at the time was very straightforward. They thought about, oh, you get kind of a partial scan as input, and from this partial scan as input, you then want to fit your parametric model to it, and then they call the shape completion in animation. It's basically just the template fitting then at test time, and they could do this with different poses and with different people at the same time. Okay, and yeah, this was, if you look at it again, this was 2005, so already also quite a while ago. And since then, a lot of stuff has happened actually. And I wanted to highlight one popular line of research that is specifically very well known in Germany. This is Michael Black's lab in Tübingen. So they're dealing with, or they basically build a lot of capture rigs that can capture humans, and from these captured humans, they build a variety of 3D models, parametric models that are being used for certain tasks of human body reconstruction. And one very popular model here is the simple model. It's SMPL, typically short, we call it simple. And this is a model that came out of that lab. And this is probably one of the state-of-the-art models right now that is very widely used in the academic community. And we're going to talk a little bit about this one today. I want to point out that these models, though, they are still the state-of-the-art in terms of when you're fitting stuff with deep learning and so on later. We're not going to talk about the deep learning stuff, but imagine the deep learning stuff later is mainly replacing the fitting terms at test time. The deep learning stuff is not replacing the parametric models, at least not for the time being, right? And this is something to keep in mind. And this is the reason why I wanted to keep this lecture this way as it is right now. I think it's very important to understand these fundamentals here first, and then you can think about what are the right fitting terms essentially in order to fit these models to some respective targets. And then you can, take strong feature matches and so on from neural networks that are very established. But for now, we're going to talk about how these models are actually being constructed, because I think this is very important and fundamental if you wanted to do research with that. Okay, so how is simple being done? Well, the core idea is kind of similar as before, right? So the question we have to ask ourselves, how do we parameterize the shape? And we have talked about two different things, right? We have talked about these PCAs. Most of the time, there's a plain PCA for the shape, and then you're going to have some delta blend shapes or so for the expressions respectively. And that that is being done for faces, it's been done for humans. And one big thing that we have to talk about right now is essentially how do we parametrize the poses, right? I mentioned now a couple of times that I've been talking about skeletons for a bit. And typically when I'm talking about a human skeleton, this means you have a bunch of joints. These joints are kind of connected. Every joint has kind of a bunch of parameters that tell you how this joint moves. It could be just the location, but it could also be a rotation in a location. And the original idea from these skeletons essentially stems by, well, we're just gonna go ahead and have a template of a human, and we're gonna have parts of that human, and we're just gonna parameterize every part separately, following the respective parts of a skeleton in a sense, right? This is kind of the idea. So you have kind of a skeleton that maps to some human, and then the human itself is kind of segmented, and you're gonna get these body parts here, right? And the very naive way to do this is you could go ahead, you could just say, oh yeah, okay, so now we're gonna go ahead and parameterize every part separately. And typically when we're talking about parametrization, it just means, well, every part just gets a rigid transformation. Rigid transformation means you can have a rotation and translation matrix. And we're just gonna say, well, the pose of this entire thing is just a concatenation of the rotations and translations of the rigid poses for every part together, right? So we have an Rj and a Tj for everything together. And in a sense, this is kind of reasonable, right? So it's reasonable for various reasons. Because now we can go ahead and in principle could map this to a skeleton, and then a skeleton could kind of animate the respective body. So we would have a very nice pose parameterization that would allow us to later on animate the mesh accordingly. And in principle, it's easy to do because we know we only have to do the segmentation once in our template model, and then we could reanimate things accordingly. Okay, so if we're doing this, what are the possible problems? Or what are the possible, maybe problems is a bit negative, maybe we should talk about what are the possible challenges. And there's a couple of challenges with it, right? So first of all, what we have to think about, if every body part here moves completely independently, right? If this arm moves independently from the upper arm here, then you're gonna get at some point disconnections, right? If they completely move independently, that will be an issue. So they have to be somewhat connected with respect to each other. So you can't just move them completely independently, because that would mean that you're separating essentially the vertices out, right? And then you would get weird stretching artifacts and so on you would have to deal with. And that's something to consider. There's a few other challenges here right now. So a few other challenges is basically, how do we go ahead and go from these parts back to the vertices, but then have kind of smooth transitions between them. So one of them I mentioned, if it's completely separated apart, that would be an issue. But you also have to think about, oh, how is this, how is the transition here being smooth, right? If I take my elbow here, right? So this part here, like it kind of moves together in a certain way. And that is something that has to be considered when we parametrizing the poses accordingly. Okay. And we're going to talk about this one a little bit. This is actually not so straightforward. We talked about a few things already, how to do this skinning, or this, yeah, from the skeleton with respect to the mesh. But I wanted to start a little bit about how do we even start parameterizing this kind of stuff. And what I would like to say here is there's many ways to parameterize it. I'm just proposing one of them that has been used many times from the folks of Simple and so on, right? And you can start very simple here. So if you're starting very simple, you could think about, okay, if a rotation matrix, it's a 3x3 matrix, that means we have 9 numbers in this matrix, which is cool. It's a matrix, but it's not necessarily a rotation matrix. So in order to make it a rotation matrix, you have to add a bunch of constraints to make sure the matrix is orthonormal, right? That's the definition of a rotation matrix. You could also go ahead and parameterize it with Euler angles. That has certain advantages and disadvantages. I'm not going to go into all the details here, but I mean, you can imagine that, that adding these hard constraints in might become later on a bit of an issue. But also leaving the numbers here as all three matrix variables and then just trying to optimize for all of them together, this is also not so ideal for the optimization. And one of the things people have been doing for a while, they use these exponential maps. And what do exponential maps mean? Well, you can simply go ahead and parametrize the rotations using these exponential maps, right? So that means you can derive it very easily, and it's a very compact representation. And and then the rotation can be obtained with this. So the rotation is defined by an angle around an axis here, right? You have the angle omega here, and this one is our axis of the rotation here, right? And then the rotation can actually be obtained with this Rodriguez formula, which is something that is very common in this field, that you can basically take this exponential map here and get back to a rotation by using this Rodriguez formula here. I'm not going to go into the math here. This is something I assume people have been introducing in our math lectures. If not, you might want to look it up, but this is something that is fairly standard. How do we go from the exponential maps back to our rotations respectively? So the transformation is then associated with, or can be associated with a rotational joint, right? So we have here, this is our joint here, and this is our matrix here is parametrized by the joint. Again, this is a joint that typically will come later from a skeleton, and then this joint here, and then you have a rotation, which is this omega angle here, right? Okay, and what that means is we have now a matrix that is basically given by the joint position. It's a translation vector basically, and we have here our 3×3 matrix for our rotation that is parametrized with the exponential map. And this is what we want to have, right? And at the end of the day, this is a 4×4 matrix. You'll see this very often in both computer vision and computer graphics, of course, right? We have here, we have the 1 here, we have 0 here, translation here, rotation here. Very standard, nothing very new. And then what we can do here is, this is essentially now our matrix that we're getting out of it, and this is our rigid body motion, how it's being parametrized. And now what we can do is, if we have the matrix given, we could go ahead and say, oh, give me a vertex that is in the influence of that matrix, and we just multiply it with that matrix, and we get the respective animated vertex based on the current joint and angle that we have. Now, this is cool for one angle. This is cool for one joint. But in practice, we're going to have more than one joint, right? We want to have a full human skeleton. And for that, you're going to have kinematic chains. Funny enough, this is not just done for human skeletons. Kinematic chains is a thing that has been used for all kinds of things, but this is kind of a special case here that we're going to look at is for the human skeleton case. So now the human motion constraints can be modeled with this kinematic chain. So if you want to make this simple right now, let's say this is an arm here, right? This arm here has two joint centers. We have J1 and J2, right? These are our respective centers here, right? And then what we want to do is we want to figure out, oh, how is this point here moving, right? And we can just go ahead and concatenate the transformations of this kinematic chain, right? And this is what's being done here, right? So now this one is one definition, and this omega 2 here moves into this direction, and so on, right? And the idea is essentially now that the total transformation G of the endpoint is just the multiplication of the two transformation matrices together, right? So in a sense, we have here this endpoint here, this P, right? And this point is based on a transformation matrix G, and this transformation matrix G has two angles, omega 1, omega 2, J1, J2, and this is just the kinematic chain here. It's just multiplying the respective parts of the joints here together, right? So we have here the first one here, which is this one here. We have the second one, which is this one here. and this is just the concatenation of these two respectively, right? So the total transformation G is just based on the multiplication of the individual matrices together. Okay, but now this is just for a single arm, right? In this case, we have two here, but in practice, we're gonna have much more. So in this case, we're gonna have post parameters that is based on a bunch of joins. In this case, we have k joins. So now what we can do is basically we can, given these definitions, we know what we need to do in order to define the motion on the full body. And now what we are assuming is, we are assuming that we having a segmentation given of the human body, which is this one here, right? And every color here is one part of the segmentation here. And what we do then is we say, okay, so we have these different colors that depict the different segmentations. Now we need to define a set of joint locations J that form a skeleton. And then what we do is we assign these joints with the respective parts of the segmentations, right? And then the motion of every part is purely rotational. And the pose of the human is fully parametrized with a vector theta that contains, this one here, we're now introducing this vector theta that contains the 3-axis angle corresponding to the rotation of every point, right? So be aware, right? These are these omegas. They are respectively 3-axis angle rotations for every joint location. And so basically this is what we have right now. So now we have again our template mesh, which is here. We have a segmentation of this template mesh. We have a bunch of joints on this template mesh. These are the J's, and we have the respective axis angles theta. Well, the axis angles are omega, but the concatenation of all of this vector is theta then. And this is essentially now defining our skeleton. Now, one thing I already mentioned, what we can do right now is we could just say, well, every part or every point on every part here is just associated with one respective joint here, right? You could do this. You have this kinematic chain as we just described it. But what we would love to do is we would not just have a nearest neighbor mapping, but in fact we want to have a smooth transition between the joints, right? So what we would like to do is we would like to say, well, if I have a point here that's kind of dependent on this joint, and that joint, right? And so what you do is you do linear blend scanning, and we've mentioned this already a couple of times in different contexts. The idea is now that if we have a point Ti here, and we want to transform it to Ti prime, the idea is essentially that we have a bunch of weights that tell us how much each of the matrices are being weighted, right? So the idea here is essentially, so you have this G matrix. One G matrix is associated to one joint. You have K of them. You go over the entirety of all of these joints here. Each of them gives you a matrix, and for every point here, you know how much does every matrix affect this current point. And what that means is we have this smooth transition between points accordingly, right? So you, like, if you're here, this point here is, for instance, 0.8 and 0.2 is a weight, and then you know how to weight these respective part transformations, right? Again, so the elbow joint, for example, would get transformed as 0.8 times of the upper arm and 0.2 times of the lower arm, right? And this is kind of just this linear reweighting, and that gives you a nice smooth transition here. Okay. Yeah, so this is linear blend scanning, of course. We know, I think we should know by now how this works. And what that means is instead of getting this like, so instead of getting this harder assignment between nearest neighbors, now we're getting the smooth assignment here between the respective targets. Okay, I want to show a quick example here. So if we're taking an example, so this is take a look at the animation results. this is basically what linear blend skinning gives you. So it goes from here to here. And this is actually, it looks pretty smooth for the most part. It has a couple of issues. We'll talk about these ones. But for the most part, you get smooth transitions because of the linear blend skinning weights. And yeah, LBS, by the way, is the short acronym for it. Like if you hear this, like this is often referred to linear blend skinning. It's very common. Okay, but if you're going to the nearest neighbor, essentially you get this one, right? And you see very quickly that, for instance, here, if you look at these transitions here, right, they look just not very good. And in order to get some continuity, you can take the linear blend skinning weights, you have the smooth transitions, and then you're getting nice animation properties. Okay, so if we're summarizing the things what we have talked about so far, a linear blend skinning model defines the following parameters. But by the way, like standard skinning is linear blend skinning, right? This is just the standard way to do skinning is linear blend skinning. That's what everybody uses. Okay, so what we have here is we have the rest pose vertices. This is our template. So we have 3 times n vertices here. We have the joint locations. We have 3 times k joint locations here. We have, for every vertex, we have a weight with respect to every joint location. So this is n times k here. Weights that tell you for one vertex, again, for every vertex, n, how much does every joint k affect it, right? And this is actually kind of important to realize that this matrix in practice is pretty sparse, right? So for instance, a point here on this one here will be only affected by the local joints and not by or like barely by anything else, right? Okay, and then we have the post parameters theta, which is our skeleton here. It's 3 times k because we have one 3-dimensional angle for every joint k, right? Okay, this is what we need to have here, right? So now we have the vertices, we have the joint locations, we have the weights, and we have the post parameters. Well, and now what we want to do is we want to put we want to have this skinning function, right? The skinning function takes as input the template, the vertices, takes the joints as input, and the weights of the linear blend skinning, the post parameters theta, and as output it gives you the respective vertices at the output, right? So this is what we want to do. So this is pretty straightforward right now. But the nice thing, what we can do right now, then at test time, we can change the, so assuming this part here is all pre-computed, right? Now we can go ahead and change the post parameters, and based on the post parameters, we can then animate our template mesh, and we can fit it to some respective targets. Okay, so if we are using linear blend skinning, and you've looked at this a couple of times, you see this looks actually good for the most part, but sometimes it has a couple of issues. So for instance here, we see a couple of issues with linear blend skinning. You see that, you know, here, this is not ideal, and this is also not ideal. So we see some artifacts here, but we basically have like some discontinuities. Well, discontinuities is maybe not the right term, but it's like this unnatural local deformations what you're getting. And the reason why you were getting it is because it's a linear function, right? It's just a linear blend between two things. But the problem is the joints here for the human is not quite linear, right? Because you have some bulging basically, right? So if I move here, like my muscles are changing, and based on the muscle changing and also the skin and the tissue changes here, that's a nonlinear deformation in practice. So it can't be fully animated with respect to these linear blend skinning weights. And this is a common thing right now what people are doing to fix these kind of things. So we can kind of think about, well, we need some correction, right? So we need to figure out, essentially, based on the pose, based on the deformations, we have to have a correction factor or a correction offset that tells us how to move the vertices to a better place. And this is something people call corrective blend shapes. So this is essentially a blend shape with a set of vertex displacements relative to the rest pose. Okay, what does that mean right now? Well, what you do is you say you're gonna have a base model here, and you're gonna parameterize offsets of the base models as delta blend shapes. Right? So you have these delta offsets with respect to the bases. So you have 3 times n offsets here. And the idea is that if you're moving, you're parametrizing these corrective blend shapes based on the pose. In other words, if you're changing the pose, you're also changing the base shape to a very small degree, right? So you're adding some offset to the base shape relative to what's going on there. Okay, how does it look like? So if you just have pose blend shapes, this looks like that. And this is a post mesh with linear blend scanning, right? There's no corrective blend shapes here. And now what we want to do is we want to apply these blend shapes, and this is the difference here. So let's have a look at the final output here, right? This is the final output. Here it looks broken a little bit, right? This one looks not right. The elbows don't look right, and this is, like you see, this one looks much more natural right now. So now we have like nice transitions on the elbow. We have nice transitions here on the hips, and so on. And what this did is basically is these corrective blend shapes. This one here is the base pose. This one just changed the base pose. So this looks unrealistic, but what it did is, in order to make the animations look realistic here, it had to change the hip size here, right? If you go back, the hips in a neutral pose look like this, but now if you're animating it, essentially, it's kind of simulating. The thing about it is like the soft tissue and muscle bulging and stuff like this, it's kind of simulating this to a certain degree. It's not physically plausible, right? Just to make this very clear. These corrective blend shapes just try to make sure we're getting reasonable poses at the end of the day. And this is kind of a cool thing. And that is basically what the simple model is doing. So all of these things together, right? So simple model is a skinned multi-person linear model. This is the simple. And these guys, they have spent a lot of effort on a multi-post database. So they have 20 males, 24 females, and they have about 1,800 registrations between them. And these are some of their database examples. So you see they have a bunch of reconstructions here. So they have basically these 1,800 registrations. These are the respective registrations that you see here. And these are single post registrations per gender, basically, right? And to train the shape-related parameters, they basically train from approximately 4,000 body scans from the US and European CSAT datasets. And then you can get this parametric model with all the tricks that I just described, with the shape for the PCA and with the expressions parameterized by the respective LBS and corrective blend shapes. Okay, these are some outputs here. This is the female principal components here that can be averaged. Right? So you can see it's has a very nice behavior when it's being animated. Same thing works on the male part. And in practice, I think the authors claim here that 10 blend shapes capture basically most of the variations. And you see that here, right? So at the bottom you see, okay, like blend shape PCA 7, PCA 8 almost doesn't change anything anymore. If I go back quickly, right, you see that the first PCA does basically the height. The second PCA does mostly like thicker versus thinner. And then the other ones, they're changing very minor parts of the shape because this is how the PCA base works. Only with a few coefficients of the few principal components, you can get a very good low-rank approximation. Okay, now you have these post blend shapes. This is these corrective blend shapes that I just mentioned. This is how these animations here look like. And this is what you see here, that the base shape changes relative to the animations here. Right? So this is what these corrective blend shapes are. By the way, finding these corrective blend shapes is also just a nonlinear optimization problem, right? There's just a way how to find, what is the optimal deformation in the base such that the respective linear blend shapes, the linear blend skinning looks as good as possible. Right. I think this is kind of cool, right? Because you see basically how the base shape changes relative to what's needed in order to make the respective animations look good. Okay, this is kind of simple. As I said, it's really cool. A lot of people are using it today. If you're working in this area, you should definitely have a look at this one. If you're working with human bodies, this is de facto the standard academic model that everybody uses in that community. Okay, a couple of more things. There's a couple of variations of this. So there's like extensions of simple. Some of them add dynamic blend shapes. This BD here is kind of a dynamic version of blend shapes. So now the offsets of the human body are dynamic. And this is in this case, this is trained from about 40,000 dynamic scans. And then they get this lowering approximation of the respective dynamics. They can also do things like soft tissue, right? They call it then DIMPLE, dynamic multi-person linear model. And this is kind of a few variations that have been done on top of simple. And you see that, now you can have more soft tissue, and they're showing quite extreme cases here. Here's another example here. So basically you can do kind of really cool things with that. Okay, so now these models have been reconstructed and have been created. Again, I'm going to give you some literature references afterwards. I can't go over all the details here, but I hope you get the core ideas. But now what you can do is you can also go ahead and do reconstructions of human bodies. So you can now go ahead and have a non-rigid registration to align to scans. So the idea basically is you're going to have a template fit to an input scan. So let's say you have a depth map, and then you typically have a bunch of data terms. Again, recall, very similar to what we have been doing in the context of human faces, but now we're doing it with respect to the simple model. And I want to go over this one again because this is just, it's very similar to what we have talked about there in the past. With a couple of different terms that are widely being used. So what are these typical terms here, right? So what can we do? Well, we have a D. What's the D term here? Well, this is a data error term, right? This says template and target surface need to match. Okay, so that you have an L2 distance between every projected surface point, right? You can have a marker term. The marker term says, oh, detect a bunch of key points in the input. Based on these input key points, try to make sure that you align as much with the marker points on the respective template. Had the same thing for faces, now it's for humans. And then you do stuff like this, transformation smoothness. You say, oh, like it's a regularization term, right? So you say, oh, don't make the transformations, don't deviate too much. But let's have a look at this one here first. This is when you use a marker term. Again, marker term here takes an RGB input image. And from this RGB input image, you get a bunch of key points detected. You can use your favorite key point detector. I don't know, what like OpenPose or MediaPipe, I think are pretty good ones that people are using today. And then you kind of have, this is a two-dimensional term. Sorry, these are two-dimensional terms here. So it's just the 2D L2 difference between the respective 2D offsets, or the 2D differences between the markers on the projected skeleton and the respective detected key points. And you're trying to optimize for the respective poses here of the template. Okay, same thing for the depth here, right? So this is a depth alignment here. So now you say template and target surfaces need to align as closely as possible. It's kind of like an ICP, right? You're trying to project it, you fit it, you optimize it, and so on. This one here is slightly different because this is actually based on silhouettes. So you can do this in 2D as well, and you can extract, have a distance between silhouettes. But this could be based on depth, or it could be based on silhouettes, right? So depth would be for every point, it's like an ICP term. Or here, in this case, it's based on 2D, and you say, oh, the respective silhouette needs to match accordingly. So I just wanted to highlight this one. This can be a couple of different variations, what you apply here. The advantage would be if you don't have depth, a silhouette term would also work. If you have depth, you definitely want to use a silhouette term accordingly. Okay, so let's have a look at some results of the reconstruction, because I think these ones are looking actually pretty cool. And this is what you can do with that basically now. Okay, so now there's some input. Again, look, this is in front of a green screen. Because of that, there can be a good segmentation. Probably with new deep learning methods, you wouldn't need this anymore, but you need a segmentation at some point, right? And then you can fit to this video stream, you can fit the respective models, you can texture it accordingly, and these are the respective reconstructions that you see. And I think that's kind of cool. They can also do this for outdoor videos. They now have to figure out to get a foreground-background segmentation, of course. And then they can fit the respective models based on these terms that we have just said. Again, here's another example. Yeah. I think it's kind of cool. Okay, so I'll leave it at here right now for human bodies. I think these results are super cool. Again, I wanted to highlight again that the core concept of the models is still state of the art here. The question is a little bit what the input is. So one question is basically how do you get the respective markers? This is something where we use deep learning methods today. Do you use depth data or not depth data? Right? If you have depth data, you have a density projection term for the most part. Or as here, you just have a silhouette term, but for the silhouette term, you need a segmentation. Segmentation, for the most part, if you do it in videos in the wild, you would do it more on a foreground-background segmentation or something like this, trained with a neural network. And there's a lot of cool follow-up work on this. I'm not going to go into all the stuff how to do the fitting better. The main motivation for me showing this was mostly how the parametric models are working. For fitting, again, there's a lot of cool things afterwards. You could probably look up yourself as well. Okay, I want to talk very briefly a little bit about hands, because the hands, it's always very similar, right? For things like when we talk about motion capture or so, we really want to get faces, bodies, and hands. These are the three most important things. So far, we've talked about faces and human bodies, but I wanted to talk a little bit about hands as well. It's not going to be super detailed, but I'm going to refer to a couple of papers you can have a look at. But I think it's kind of important to make the connection here that this is essentially borrowing similar ideas from the other two respective domains, right? So what do people do for hands? Well, we have similar ideas. So we have statistical models. We can anchor the models with respect, or parameterize the models with respect to a skeleton. We have some sort of training data to compute the parametric models for hands. These are typically either offline scans. It turns out this part is a little bit different for the most part, and for hands, at least historically speaking. So for hands, people most of the time or often actually use synthetic data to construct these models. And this is kind of funny because the reason is simple. The reason why people using synthetic data here often is, like, scanning a hand is actually quite difficult. And getting a good non-rigid registration for a hand is not as straightforward. So what people have been often doing, they're using basically synthetic training data here. And then they kind of procedurally generate new hand animations. And based on that, they're computing parametric models, which is kind of an interesting thing, how to do that. Not going to go into that detail, but I wanted to point it out that the same concept of using a high-end laser scanner used to be a little bit harder for hands because the non-rigid registration becomes a bit harder. But the idea is still similar, right? You have still a statistical model, you have anchored skeleton, you have some training data, and then the test time, in a sense, you're fitting it to some. You have this lower dimensional model, and the fitting works in this lower dimensional parametric space, right? Okay, so what are the things we have here? Well, we have a pose prior, we have a shape prior, we have beta and theta in a sense. We're gonna often get some sort of PCA basis in the shape, and the poses are most of the time some human skeleton accordingly. And There have been a lot of different hand models that people have been looking at actually. And you see roughly what the timing is here also. So the timing here goes from 2011 to 2016. This was the kind of the golden time when people handcrafted hand models. And there's also a reason why that came up right at this time. And it's often driven by some economic factors. And kind of what's funny is like everybody was looking into VR at the time. You're still looking in VR, it's still very important, of course, and it's kind of an interesting future avenue. But basically, people had to get hand tracking right and had to get hand reconstruction right. And for like AR, VR, this is like super, super critical, like on a HoloLens, on Oculus or so on, getting hand tracking right. And this is kind of was in this era. That's why there were a lot of hand reconstruction and hand tracking people coming out of it. Again, there's a lot of follow-up work comes afterwards, but then people look more into how do we use deep learning for fitting terms in order to get better fits for the respective targets here. Okay. What's the difference between these models? Well, these models are relatively similar to some degree. They most of the time differ in terms of their respective base parametrizations, base methods. They have some parts for the most part, and yeah, then they're decomposed with different parametrizations. Some of them use similar things what we've just seen for simple with this linear blend scanning. Some of them use different techniques. I wanted to highlight this Taylor paper because this one I really liked a lot. What they do is kind of funny. They use a subdivision surface model. So the graphics people know what subdivision surfaces is. So there's like Cadmore-Clark and loop subdivision surfaces. And the idea of subdivision surfaces is that they are mostly C2 continuous. And C2 continuous means you can compute the derivatives twice, right? And you can get second order derivatives out of it. And one of the things that these guys exploiting here is that they use these second order derivatives for good fitting with the Levenberg-Marquardt fit. And because of that, they can get really, really good convergence and fast optimization speeds. And here you see a couple of visuals of this method, actually. So what they're getting is essentially a bunch of sparse depth points as input, or like Kinect style input points. These are these ones here. And then what they do is they can fit the hand model respectively to the target. And you see how quick that fit is here. This is just a few iterations with the second order solver here that allows you to fit the hand model, this parametric hand model, to the respective target points. And I think that's kind of cool. And these are the results what they're getting essentially here. These are some data sets like Dexter, Fingerpaint, NYU. These are popular hand tracking data sets. So they have the Kinect input there, and then they can fit the respective hands on top of it. So I can highly recommend have a look at this paper because I think it's kind of cool how they do it. Another important thing, what people are looking for is this like online calibration in the sense of hands, because every hand slightly differs, and then people trying to figure out, oh, how can this hand be calibrated such that the shape here is fitting better. This is from Andrea Tagliasaki's group. He's actually a professor right now in Vancouver, and I think that's also really cool work actually. So he and his group, this was a paper by Anastasia Sack. She worked on this for quite a while, and they have done some really cool models that they can do real-time fitting, and in this work actually they do this online. They do this online optimization essentially of the pose of the shape as well, which they call calibration, and based on that they're getting very accurate fits to a bunch of sparse depth points. Again, you see here the depth points, and they're fitting this model essentially here at test time to it. Okay, so yeah, I'm not going to go into much more technical detail. I think I'm going to leave this for the reading homework. But I think this is kind of cool. If you wanted to work in these areas, especially with deep learning methods, this is the stuff to study first, because then you know what are the things you can learn afterwards. And learning today means mostly what kind of features can you use here to get faster or better convergence actually. Okay, there's also people who tried now to combine bodies and hands. there's this Mano model that is kind of human bodies and hands combined. There were also some attempts to combine humans, bodies, and faces. And yeah, the motivation video here was that basically they say they have bodies and humans, and now they sorry, bodies and hands, and now they want to argue why they can combine the two together. So I hope this video is not too long, but yeah, so the idea is right now that they wanted to have here the hands being integrated essentially in the body model, and then they treat the two separately, and they have a nice way of combining the two directions here. Also very cool to do. So they have this Mano paper, which is kind of nice. Okay. Yeah, a couple of things maybe to summarize here. So I think the main goal of this and the last two lectures was to give you a bit of a hint how these models are being generated, like how to figure out essentially how do you generate parametric models, and then decide which are the energy terms for fitting afterwards. And the one thing you have seen always is that we need a lot of training data to construct these models. And most of the time, these training settings are basically, they're based on some sort of scanning setup, right? So you have a bunch of laser scanners, or you have a bunch of Kinect scans, and then you collect some data, and then you compute some sort of low rank approximation from it to have a lower dimensional parameter space to capture the variations in the respective high-end scans. And there's a couple of things that I haven't mentioned too much, but that's something you have to be aware of. The way these models are typically constructed, we always have these things that there's the neutral pose between subject is often similar, but it's not perfect, right? So this is one of the things that is very challenging, because if I'm gonna get 10 people into a laser scanner and I'm gonna tell them, oh, make a neutral face, they're all gonna make a different neutral face, or they're all going to make a different neutral body pose. It's not always going to be perfect, and this makes often a bit of an ambiguity here, right? And when you do fitting afterwards, you have the same issue actually. You get this ambiguity whether is this now a pose change or is it just a different shape change? This is also still a pretty critical thing when these models are being fitted afterwards, like how to distinguish between those two. And practically, people now use a lot of regularizations in order to address these challenges. Okay, we have drift and non-rigid registration. That is an interesting thing that basically, if this happens, you're going to get a bunch of PCAs that don't do anything. Because basically what this means is, so let's say I'm going to fit something to my body, and like my t-shirt or so would slide a little bit like this. So the global shape would be pretty similar, but the vertices would slide across the surface. So the shape is the same, but if you're computing now a PCA off top of the vertices, you would have this issue that some PCA capacity would be allocated for this drift. And that's an issue that is really hard to prevent. So if you want to create good models, you most of the time have to fix this drift part first. Otherwise, you're going to have free parameters in your model that are not really relevant to any outputs. Okay, so I wanted to give you a few links. This is by far incomplete, but I would like you to have a look at these ones. So the CISO database we managed, SCAPE we managed, Simple we managed. SCAPE and Simple, these are must-read papers for you, right? I wanted to highlight these papers you should have read for the exam, and we expect them to have a good knowledge of these two papers. This is just so fundamental to many things. There's a couple of new papers coming out with deep learning. This is not so relevant right now academically for the exam, but it's super relevant if you're interested in doing research in this area, like PIFO and NASA. These are really cool papers that now start using deep learnings for either model learning or for fitting purposes afterwards. So this is something if you're interested in the area, this is really cool, I think, what you can now do with deep learning and so on afterwards. I wanted to leave it out for the sake of the, being a bit more concise of the content of this class. This is not necessarily a deep learning lecture. We're having deep learning lectures also. If you're interested in, ideally you can combine the knowledge of these lectures. But this is something, if you want to do research, I think these are cool papers to look at. And then I wanted to give you an overview of the hand tracking papers. So this one I mentioned. This is a really cool tutorial by Andrew Fitzgibbon and Jonathan Taylor. So they talk about how to do these kind of things right. And these are a couple of very interesting hand models and hand fitting works that have been done, pretty much doing the state of the art for model generation for hands. For fitting, people have now used a few more deep learning things, but the models are still, I think, pretty much what everybody's using today, even though we have better fitting terms. So yeah, maybe have a look at these ones as well. I think they're really fun to read, and there's a bit of overlap, so it's not like you're reading every time a completely new paper. Especially this tutorial here is something I expect everybody to have a look at. All right, then thanks a lot. This is the conclusion of the lecture right now. Thanks a lot for tuning in, and I hope you have some fun doing the reading homeworks and you're also enjoying the cool research results that these methods have managed to produce. Thanks for joining. Bye-bye.